Hello and welcome to the world of heavy minerals. In this video, I'm going to talk about the features you should observe if you have to identify heavy minerals by optical means, that is, by using the polarization microscope. Once you went through the process of separating your heavy minerals, you end up with a heavy mineral concentrate. From this concentrate, you will produce strewn slides by embedding your grains in some kind of mounting medium. For my videos, I'm always using melt mount with a refractive index of 1.662. The difference of strewn slides to normal thin sections is that they do not get polished, which means that the grains will have different thicknesses. Therefore, the optical description of heavy minerals is slightly different from what you're used to in thin section description. However, you are still using the polarization microscope, so many of the principles that you learned in your polarization microscopy class still apply to heavy mineral identification. A really valuable resource is the book Heavy Minerals in Color, written by Maria Monge and Heinz Maurer, which is basically an optical guide to heavy mineral identification. Under the microscope, you're going to observe two sets of features, the ones observed in plane polarized light and the ones observed in cross-polarized light. In plane polarized light, we observe the color, shape, cleavage, relief, inclusions, and pleochroism. In cross-polarized light, you will observe the birefringence, isotropy, extinction, and elongation. The latter two are only observable in elongated minerals. Let's start with the features observed under plane polarized light. Color is rarely diagnostic for most heavy minerals. However, there are some exceptions. For example, the grayish-blue chloritoid, golden-yellow staurolite, green epidote, and blue sodic amphibole. Then you describe the shape of the mineral. Grains may be euhedral, prismatic, irregularly shaped, platy, round, or angular. Next, you will look for any linear features, such as these cleavage traces, striations, or lamellar twinning features. When it comes to describing the relief, we usually differentiate between low, moderate, and high relief. This is easiest if you have many different grains next to each other, so you can observe the difference. For example, here we see a tourmaline grain with low relief, marked by its thin outline, versus a garnet grain with a high relief, marked by this thick black outline. If your heavy mineral has inclusions, make sure that you characterize those as well. You could have fluid inclusions, mineral inclusions, or graphite inclusions. Pleochroism means that if you look at your mineral under plane polarized light and you turn the table of your microscope, the mineral changes color. This tourmaline grain shows extreme pleochroism from light brown to almost black. Let's move on to cross-polarized light. First, you will check the birefringence, or the interference colors. Here we have an apatite grain with first-order white and yellow colors, a kyanite grain with first to second order colors, and zircon and monazite, which have very high order interference colors. Some minerals show anomalous interference colors like this titanite grain with its sky blue tint. If your grain stays black under cross-polarized light, even if you rotate the table, it means it is isotropic. This is characteristic for the garnet and the spinel group. In elongated minerals, there are two more features to observe. The first one is called extinction. To observe the extinction, you rotate your mineral into a north-south position. In this example, this tourmaline grain is extinct in this position. This is called parallel extinction. In this example, the grain is not extinct while oriented in a north-south orientation. Instead, the mineral has an extinction position oriented in a certain angle to the north-south axis. This is called an inclined extinction. You can read the extinction angle using the nonius, which should be attached to your microscope table. In this grain, this angle is rather large, around 35 degrees, which is typical for clinopyroxenes. The second feature you can observe in elongated minerals is called elongation. It can be either positive or negative. To determine if your mineral has positive or negative elongation, you will need the Michel-Levy color chart and the accessory plate of your microscope, which in my case adds 530 nanometers of optical retardation. Then you rotate your mineral into a northeast-southwest direction. In this example, the lowest interference color at the rim of the grain is that of a first-order light gray, around 200 nanometers. If I add my accessory plate, this will add 530 nanometers of optical retardation. In this example, the interference color changes to yellow of the first order, around 330 nanometers. The math I have to do for this result is 530, which is the optical retardation of my accessory plate, minus 200, which is the gray colors of the first order. This will give 330 nanometers, the yellow of the first order. Because I use a minus, this is called negative elongation. In the next example, we start again by rotating the mineral into a northeast-southwest direction. Again, the mineral exhibits first-order light gray colors, so again around 200 nanometers. If I add the accessory plate, the color changes to blue of the second order. The math I have to do for this result is 530 nanometers of the accessory plate plus 200 nanometers of my first-order light gray. This will give 730 nanometers, which is the area of second-order blue. Because I use a plus, this is called positive elongation. These are the most important features to observe under plane polarized and cross-polarized light. In the next videos, I will show you some of the most important heavy minerals and walk you through their optical characteristics.